combination of resistances. When it comes to combine springs, coils, condensers, and these resistance wires, always you have two options in particular, that series and parallel. Then you have another option of having a mixed combination in which series might be greater in number or the resistances in parallel might be greater in number. Let's go one by one. Series combination, the resistances one by one are connected. The current is going to be same through all, but you see the current always advances from positive to negative terminal, and in the direction of current the potential will always go on decreasing. You see, when the current passes through resistance, the potential will fall. So it's not exactly below this, but for this resistance, the fall of potential has been shown over here, this thing. And for this resistance, fall of potential has been shown over here. In the conducting air, we simply assume that there's no resistance, and that's why the potential will not change compared to or corresponding to this connecting wire. In series combination, total potential will be added. Potential difference on each is going to be combined in order to get the total potential difference or the voltage. Similarly, the resistance will be R1 plus R2. For n equal resistances, it's going to be NR. If you want to compare the potential difference across the resistances, it's going to be R1 upon R2. The heat will be combined, and you want to find the ratio, it's going to be again R1 upon R2. You see, since the current is equal in all the resistances, then in that case, current which is equal to J into A, it's going to be constant. That means J1 A1 will be equal to J2 A2. Parallel combination. Now, parallel combination, the voltage is going to be same throughout, because parallel means itself that one end of every resistance will be connected at one point, the other ends will be connected at one point. Obviously, the potential difference between the 2 points is going to be same throughout. Then V same, but the current will be in the inverse ratio of resistances. Then this heat produced will also be in the same ratio. Heat will be added Q1 plus Q2. The current will be added I1 plus I2. The total or equivalent resistance you are going to get as 1 upon R1 plus 1 upon R2. Equivalent value you are going to have R by N if there are equal resistances. Then you see in parallel combination V, that is IR. IR is going to be constant, better you write I, J into A, this R, rho L upon E. E gets cancelled. When you say in parallel combination, voltage is constant, that means rho into L, J, this is constant. If you are having same materials wire, then obviously J into L will be constant in parallel combination for all the branches. That's given over here. One thing you have to remember, in series combination, the equivalent is going to be greater than the biggest value in resistances. Similarly, in parallel combination, you'll be getting the equivalent resistance less than even the smallest value in the sets given there. If you are having equal resistances, the number of maximum possible combination will be 2 to the power n minus 1. And if you are having n different resistances, it's going to be 2 to the power n. Suppose you are having n resistances, then in series and parallel you connect and find the equivalent. The difference of the two is going to be R n square minus n upon n.